In August 2012, a probe built in the 1970s crossed out of the Sun's protective bubble, and the first thing it found was that space had gotten denser. Not emptier, denser. The plasma around it jumped roughly 40 times thicker than the region it had just left. Every model said that number should level off out there. It didn't. It's still climbing today, more than 19 billion kilometers from home. And it was only the first of 3 things Voyager found at the edge that we still cannot fully explain. Space got less empty. To understand why that one measurement unsettled people who had spent their careers on it, you have to know what the probe was and where it was standing when it sent the number home. There are 2 of them. Voyager 2 launched on the 20th of August, 1977. Voyager 1 launched 16 days later, on the 5th of September, which means the lower number actually left second. They were built to photograph planets. Jupiter, Saturn, Uranus, Neptune. That was the entire job. Nobody who designed them was thinking about interstellar space, because in the 1970s, nobody could even ask the questions these probes ended up answering. Nobody built it to answer this. So what did Voyager cross in 2012? Not the edge of the solar system. The sun blows a constant wind of charged particles outward in every direction, and that wind carves a bubble out of the galaxy, the heliosphere. Far out, where the wind's pressure finally balances against the thin gas between the stars, it stops. That balanced surface is the heliopause. It is the edge of the sun's wind. It is not the edge of the sun's gravity. The sun still holds comets out in the Oort cloud, roughly 100,000 times farther from us than the Earth is. By that measure, Voyager won't actually leave the solar system for something like 30,000 years. It crossed a boundary. It did not go home. And the boundary is far in a way that's hard to feel. Sunlight reaches Earth in about 8 minutes. At the place where Voyager 1 crossed, sunlight takes roughly 17 hours to arrive. And a command sent from Earth takes about 22 hours to reach the probe, one way. You ask it a question at breakfast. The answer comes back the next morning. A command takes 22 hours. One more detail matters before the anomalies begin. It's the reason this story is more than a single broken measurement. The 2 probes crossed in completely different places. Voyager 1 punched through in the north. Voyager 2 punched through in the south. 6 years later, 67 degrees of latitude away, on the far side of the boundary. That separation is the whole point. Anything only one probe sees could be a local eddy, or a fluke of one spot. Anything both probes see is a property of the edge itself. Hold on to that. It pays off twice. So when Voyager 1 finally crossed in 2012, the first measurement it sent back should have been the simplest of all. The plasma should jump to interstellar density and then settle. That is not what happened. The boundary gave them a number, then refused to behave like a clean boundary at all. Start with how a half-blind probe measures the emptiness around it. Voyager 1's direct plasma detector died in 1980, decades before the crossing. So it cannot taste the plasma. Instead, when a shockwave from the sun rolls all the way out to the boundary, it makes the electrons there ring. They oscillate at a frequency that depends only on how densely they're packed. Don Gurnett's team reads that pitch and works backward to the density. It's like striking a bell in the dark and knowing its size from the note. To be clear, that's not literal sound. It's electric oscillation. The Voyager hum you may have heard online is a data sonification, not a recording. Inside the sun's bubble, the plasma measured about 0.002 of a particle per cubic centimeter. Then Voyager crossed, went quiet, and waited. In the spring of 2013, a solar shockwave reached it and lit the plasma at around 2.5 kilohertz. The team worked the number backward and got roughly 0.08 of a particle per cubic centimeter, 40 times denser than the bubble it had left. Don Gurnett's words: "We literally jumped out of our seats when we saw these oscillations. They showed us the spacecraft was in an entirely new region." The drama is easy to misread, so say the number plainly. 0.08 of a particle per cubic centimeter is still emptier than the best vacuum we can build in a laboratory on Earth. Interstellar space did not become crowded. It became less empty, exactly where every model said it should become more empty. The wrong direction. And then it got stranger. Voyager 1 didn't hit that denser step and level off. From 2013 onward, every new shock reading came back higher than the last. Higher in 2014, higher again the year after. The most recent readings, past 146 astronomical units, show the density still climbing. Picture wading out from a beach, expecting the water to get shallow, and instead it keeps rising, past your waist, past your chest. No one can tell you where the drop-off is. That is what the density curve does. It just keeps going up. Nobody knows where it stops. For a while, you could wonder whether the half-blind probe was simply wrong. Then Voyager 2 crossed in 2018, and its plasma detector had survived. It measured the interstellar density directly, about 0.04 of a particle per cubic centimeter, give or take 15%. No shockwave needed. It confirmed the rising wall by an entirely independent method. And in 2021, Stella Ocker found something quieter still. A faint, continuous emission coming off the plasma itself. It was a steady tone that let Voyager track the density not just in shock-lit flashes, but continuously across roughly 10 astronomical units. In her words, it's virtually a single tone. The way the frequency moves around tells us how the density is changing. The rise wasn't an artifact of occasional solar shocks. It was real, and it was persistent. So the models are wrong about something. They predicted the density would plateau, or even fall, just past the boundary. Instead, there's a sustained rise over tens of astronomical units, a pile-up, a layer, or a large-scale gradient in the galaxy itself that nobody had drawn. The mechanism is genuinely unresolved. The wall is real, the trend is still visible, and we don't know what's building it. A rising wall of plasma is strange, but the second measurement should have marked the crossing most cleanly of all, and it nearly convinced the team Voyager hadn't crossed at all. This one is harder to feel, because the anomaly isn't something that happened, it's something that didn't. Inside the heliosphere, the magnetic field belongs to the sun. The solar wind drags it outward, and the sun's rotation winds it into a spiral, the Parker spiral. Outside, in interstellar space, the field belongs to the galaxy, and it points a different way. So as Voyager crossed the boundary, the field direction should have swung. It should have rotated to line up with the galaxy. That turn was how you'd know, beyond doubt, that you'd left the bubble. In August 2012, the field strength roughly doubled and went extraordinarily smooth. Voyager had clearly crossed something, but the direction barely turned. It stayed locked to the sun's spiral, pointing very nearly the way it had pointed inside. Leonard Burlaga, who reads that instrument. A day made such a difference, the field suddenly doubling, becoming extraordinarily smooth. But since there was no significant change in direction, we're still observing field lines originating at the sun. That missing turn caused a year of doubt. The field looked so much like the inside of the bubble that the team first concluded Voyager had not reached interstellar space. Maybe it was sitting in some new pocket of the sun's own region. Maybe the boundary was stranger than expected. The absence of a turning field actually delayed the announcement that Voyager had crossed at all. The strange part was never what the compass did. It was what it refused to do. You could have called that a fluke of one location. Then Voyager 2 crossed in 2018, 67 degrees of latitude away, in a completely different patch of the boundary, years apart in the solar cycle, and it saw the same thing. The strength jumped. The direction stayed parallel to the sun's spiral. 2 probes, 2 hemispheres, the same stillness. As Burlaga put it, we could dismiss that as coincidence in one case, but we can't do that twice. We can't do that twice. And the field they're reading is almost nothing. The magnetic field at Earth's surface is around 50,000 nanotesla. The interstellar field Voyager measures is about half a nanotesla, roughly 100,000th of what a fridge magnet sits in. We are reading a faint magnetic whisper in the galaxy with a 1970s instrument, more than 19 billion kilometers from home. So what does the stillness mean? If the galaxy's field were truly separate from the sun's, it should hold its own direction right up to the boundary. The near-perfect alignment, seen globally by both probes, means either the two fields are somehow coupled across the edge, or the geometry is far larger and stranger than the textbook allowed. The leading explanation right now, from work by Jamie Rankin and colleagues in 2023, isn't that a law broke. It's a matter of scale. The heliosphere may be so large that it drapes the galaxy's field around itself long before the boundary, bending it to match the bubble's shape. Both probes may still be inside that draped layer. Over the coming decades, the field should slowly undrape toward its true galactic direction. That's a leading model, not a closed case. It's the science working on the problem in real time. A rising wall, a field that wouldn't turn. Strange as they are, those are at least things Voyager could measure directly. The third anomaly is stranger, because it's about something the probes can never measure directly. The shape of the thing we live inside. For more than 50 years, the heliosphere has been drawn like a comet. a rounded nose facing the direction we travel through the galaxy, and a long tail streaming behind us for thousands of astronomical units. That comet picture goes back to modeling work in the early 1990s, and it has been the default ever since. It's in textbooks. It's the picture in your head right now, probably, if you have a picture at all. Voyager's crossings put hard constraints on that picture, and some of them don't sit easily. Both probes saw galactic cosmic rays jump and solar particles fall away in clean, near-vertical steps. At Voyager 1, the count of galactic cosmic rays climbed about 9% in a matter of weeks. But the behavior along the flanks was lopsided. The two crossings leaked in opposite directions. At Voyager 1, interstellar material was leaking inward. At Voyager 2, solar material was leaking outward. Tom Krimigis, who reads those particles, Voyager 2 crossed where material from inside the bubble was leaking out into the galaxy. That was very different from Voyager 1. We don't yet know exactly why, and the models haven't been able to explain it. Then, in 2020, Merav Opher's team modeled the boundary a new way, tracking the hot, fast ions separately from the cold solar wind. Because those hot ions dominate the pressure but escape quickly once past the inner shock, the whole bubble deflates in the model. It loses its tail entirely and ends up compact and nearly round with two short curling jets. They called it a deflated croissant. That is a leading recent model that erases the tail. It is not established fact. Other groups, notably Nikolai Pogorelov's, still favor a long extended tail. The shape is inferred. It has never been measured. The remote evidence leans toward the compact picture. From near Earth, missions like IBEX and Cassini map energetic neutral atoms, particles born at the boundary that fly home in straight lines, letting us photograph the distant edge from the inside. Both saw structures that fit a rounded, bubble-like shape better than a long tail. IBEX also found that we move through the local gas slowly enough that there's probably no violent shock ahead of us, only a gentle bow wave. That is the humbling core of it. Voyager 1 and Voyager 2 have sampled exactly 2 points of this boundary. 2 microscopic punctures, both near the nose. The tail, the part that's actually in dispute, is something no probe can reach. We are trying to draw the shape of an object tens of billions of kilometers across, from 2 pinpricks of light coming through opposite walls of a darkened cathedral. 2 pinpricks of light. A mission called IMAP is built to map that entire boundary in neutral atoms at high resolution and finally constrain the shape. Until it returns its data, the object we live inside may look nothing like its most reproduced diagram, and we cannot yet say which picture is right. 3 anomalies. A wall of plasma that keeps rising. A field that won't turn. A shape we can't draw. And the honest thing to say about all 3 is the same thing. It was supposed to thin out. It got denser. The field was supposed to turn. It held its line. The shape was supposed to trail behind us. It may have no tail at all. Name what's actually open, plainly. Why the density keeps rising is unresolved. It could be a pile-up layer far deeper than expected, a depletion zone Voyager is slowly leaving, or a real gradient in the galaxy itself. No consensus. Why the field stays parallel is unresolved. It could be a geometric coincidence, or genuine draping at enormous scale. Both probes seeing it 67 degrees apart strengthens the draping case, but it doesn't settle it. And the shape is the most contested of the 3. And the one we may not resolve until IMAP finishes its map. This is not the story of scientists being baffled. It's the ordinary, humbling shape of a frontier. We sent 2 probes further than anything we have ever built, and the data they returned didn't close questions. It opened harder ones. Every answer opened 3 more. And consider what's doing the measuring. A field of half a nanotesla. A plasma 40 times thinner than a laboratory vacuum. A 1970s instrument, more than 19 billion kilometers away, with one of the 2 probes effectively half-blind since 1980. That any of it works at all is the quiet awe underneath the dread. Space got less empty, and we still can't say why. The probes are still going, the density is still climbing, and somewhere out ahead of them, the real, undisturbed interstellar medium is still out of reach. Voyager won't stop. The density it reads will keep rising for years. Neither probe will reach the undisturbed gas between the stars in any of our lifetimes, and neither will leave the sun's gravity for 30,000 years. They crossed the edge of the sun's wind, not the edge of its reach. We built 2 machines to take pictures of planets. They became the first things we ever sent past the edge of the sun's bubble, and the further they reached, the less we understood. That isn't failure, That is what the edge of knowledge actually feels like. If you enjoyed this video, consider subscribing, and I'll see you next time.